So far, we've talked about the structural properties of the membrane. We've reviewed the phospholipid bilayer. We've talked about the forces that act on particles that want them to move across the membrane. So in part two, we're going to shift gears and talk about the actual movement of said particles across the membrane. And more importantly, what are features or properties of the membrane that lend for that transport? Okay, so we're going to move into part two of this. And our two objectives here, we're going to first start out by identifying the three general factors that influence the rate at which a substance can be passively transported across a membrane. And then we're going to identify two general factors that influence the rate of active transport. So in doing so, we'll kind of distinguish what's active transport versus passive transport, and then we'll talk about factors that will influence them differently. Now, when you think about the rate of transport, what's happening across a membrane? So in any given scenario, if we have a differential of a proportion of particles across a membrane to which those particles are permeable, we're going to see movement in both directions, okay, which we can refer to as one-way flux. Now, that is to say that particles are moving in both directions, but there's no net accumulation on either side. And so in this instance, we can say that the particles are at diffusional equilibrium. And this is where particles strive to be. As long as they can move through the membrane and the membrane is permeable to the particle, they will move until they are at equal concentrations on both sides of the membrane. And although there's one-way movement, one-way flux, there's no net accumulation on either side. So this is what diffusional equilibrium looks like up here. So we have 1 mole of concentration on the left here, and then 1 mole on the right, even though there's one-way flux from side to side. And at the bottom, this is what happens if we have a concentration gradient. So now we have a greater number of particles on the left in side 1, and then a smaller number, 1 mole, so this is about half the proportion of particles on side 2. And so now we have what's called a concentration gradient. And we spoke about this earlier when we talked about the chemical driving force. So the chemical driving force is sort of built on this gradient. And here, particles are going to begin to accumulate. So there's one-way flux from both sides, but in the middle, the large arrow tells us that there's going to be a net accumulation of particles moving from side 1 to side 2 because we have a concentration gradient. Okay, so it's really important to think about these forces that we discussed earlier, how they can now act on particles to move the particles to become at equilibrium. All right, now let's talk about the membrane and the types of movement that we can see across said membrane. So passive transport we described as being spontaneous earlier. We said no energy was required. We compare this to being a downhill type of movement, whereas active we said was the opposite. Now, the different types of passive transport that we have are simple diffusion, and this means that particles can move right through the membrane. The membrane is permeable to the particle, and that is simply diffusing across the membrane. All right, and it's going to be aiming to get to that diffusional equilibrium that we just described. The second type of passive transport is facilitated diffusion. And the word facilitated here helps us understand that this needs some type of help. So we can move particles through the membrane, but they do need a transporter to be a part of facilitated diffusion. And then the third type of passive transport is diffusion through channels. So here we also need some type of help in order to get these particles through because they are not permeable, or the membrane is not permeable to them, but this is in the form of a channel instead of a transporter. So these are all examples of passive transport. I want you to kind of think about that as a general category in that particles are moving through the membrane, but the passive here means that they're moving down their concentration gradient. from high to low concentration, and this is considered spontaneous. It doesn't always mean that they're going through the membrane without help. It just means that they're moving according to that gradient. Now, when you think about simple diffusion, this is a specific type of passive transport where no membrane proteins are needed and particles can move right through the lipid bilayer. We've talked about this earlier as well, the fact that hydrophobic or lipophilic substances or particles can move through the phospholipid bilayer. So they are examples of particles that can move by simple diffusion. They don't need any proteins, carriers, channels, etc. What are the factors that will affect the rate of simple diffusion? First of all, the magnitude of the driving force. How strong is that chemical driving force, or how strong is the difference or concentration gradient? The second factor is the membrane surface area, how much membrane is exposed for the movement of particles. That will definitely determine the rate of simple diffusion. And then third is the membrane permeability. Again, if we have a particle that cannot go through the membrane, the rate of simple diffusion will be 0. We have to have a particle that the membrane is permeable to in order to think about simple diffusion. So here's where we don't want to conflate passive transport with simple diffusion. Simple diffusion is just an example or a type of passive transport where no carriers or transporters are needed. So those are the three factors that are going to determine the rate of simple diffusion across the cell membrane. So let's illustrate that here and look at how those three different factors affect the rate of simple diffusion. So the three factors we mentioned was the magnitude of the chemical driving force, okay? Basically the strength of the concentration gradient. So we talked about this force before, and the strength of that will determine the rate of simple diffusion. The second factor we said is the permeability of the membrane to the particle in question. So the permeability of the membrane to the particle, okay? And then lastly, the amount of surface area that is available for exchange. So the surface area available for exchange or transport, right? For exchange. So these are the three factors. Actually, I'm going to write that at the top here. Factors that affect the rate of simple diffusion, okay? And these are the three factors that we just listed. So let's illustrate that. Let's say we have three different scenarios here. And we have in scenario A, B, and C. Now there's a membrane that is separating both parts of these containers. And we want to think about this membrane as being permeable to the particle in question. So that's the first factor that's going to determine the weight, right? The membrane must be permeable to the particle. In scenario A, we have 1 mole of particle dissolved in this solution, right? 1 mole. On the right side, 0 mole, okay? So in scenario A, we're going to have a strong differential, right? We have more particle here, 0 particles on the right, so we have a strong driving force moving particles from left to right. Scenario B, we have a slightly weaker driving force. Why? Because we have fewer particles. Let's say we had 8.8 moles dissolved in this solution, and then 0.5 moles dissolved in this solution, we still have a concentration gradient, so we still have a driving force, but as we can tell, it's much weaker, right? It's going to be much weaker than scenario A. And then in the scenario C, let's say we have an equal amount of concentration of particles on both sides, zero point 0.5 moles and 0.5 moles. So here, as we would imagine, we don't have a net accumulation, but we do still see one-way movement from one side to the other. So this scenario can be described as being at diffusional equilibrium, okay? So let's illustrate that here at the bottom. So in scenario A, we have a very strong concentration gradient. Therefore, we have a strong driving force, strong chemical driving force. And so we're going to have an increased rate of simple diffusion, okay? Because the magnitude of the chemical driving force here is stronger. In scenario B, we have a weaker chemical driving force. Okay, this should have been a smaller arrow. This is a weaker chemical driving force, right? Which tells us there's still going to be movement and net accumulation from side one here to side two, but it's going to be a smaller or weaker magnitude, therefore a smaller or weaker force, okay? So let's describe this as being a medium chemical driving force, therefore a medium rate of simple diffusion. And then in scenario C, I want to make it clear, it's not that we don't have movement. We still have one-way flux from one side to the other, but we have no net accumulation, right? So this scenario can be said to be at diffusional equilibrium. So the chemical driving force here is equal to 0 because we don't have a concentration gradient. Therefore, we can say that we're at diffusional equilibrium. Okay. We can also say that the rate of simple diffusion is equal to 0. Okay. So there's no concentration gradient. Therefore, there is no rate of simple diffusion. All right. So any questions on this? Any questions on the factors that affect simple diffusion here? And then how that applies to the concentration gradient, which is the magnitude of the chemical driving force. Okay. All right, so let's keep going. Let's keep discussing the factors affecting the rate of simple diffusion, and we're going to look at them individually and illustrate some examples. First off, the magnitude of the driving force. And we can see this linear graph, this linear curve that represents the relationship between the concentration gradient and the net flux. So as the concentration gradient increases, the net flux or net accumulation also increases. That is to say that the concentration gradient and net movement is directly proportional, okay? So as big as that gradient will get, that's as strong as the magnitude of the driving force gets, and that's the more net accumulation of particles that we'll see. The second factor, the membrane surface area. So the more membrane surface area that we have exposed, the more we increase the rate of simple diffusion. And here's an interesting example in our physiology. Here's the alveoli of the lungs. On the left, we can see what the normal alveoli look like. So these little air spaces or alveolar spaces that we can see. Notice how it's giving this very large surface area for exchange. The more alveolar wall that we can see means that there's more area for oxygen and carbon dioxide to diffuse across. So there's more surface area available for the exchange of gases in this normal lung. On the right, this is what we look like when we have collapse of the alveoli. Okay, so certain pulmonary diseases like emphysema will actually start to destroy the walls of the alveoli, and they sort of collapse on themselves, and these air spaces become bigger. Not only do they get larger, but the walls, the surface area for exchange decreases. And so this is an example where because we have less surface area, gas exchange is going to be impacted, and that's going to lead to other consequences for respiration, right? This is going to be more detrimental. And this is where we see these types of effects in smokers or people with chronic airway irritants or exposures, and that will lead to decreased oxygen transport across the membrane of this lung. All right, so here's a very real example of how the rate of movement across a membrane is impacted by the amount of membrane or surface area that's available for that particle to move. And then lastly, the third factor that affects the rate of simple diffusion is the membrane permeability. Now, under the membrane permeability, we can think about some other factors. So some sub-factors that will affect the membrane permeability in and of itself. That includes the lipid solubility and of the diffusing substance. So as we discussed earlier, the phospholipid bilayer is such that only lipophilic substances or hydrophobic fatty substances, that is, can go through the membrane. So they have to be lipid soluble in order to participate in simple diffusion because these are particles going right through the membrane without any help. So if we have a lipid soluble particle, it's going to be more permeable and it's going to increase the rate. Second is the size and shape of the diffusing particle. We said this before, large, bulky, charged particles cannot go through the membrane. So even if they are at a higher concentration on one side and a lower concentration on the other side, even if we have a gradient and a very strong concentration gradient, if the particle is not permeable to the membrane because of its size, shape, charge, or lipid solubility, the rate of simple diffusion will be equal to 0. So the size and shape of the particle will determine whether or not the membrane is permeable. Number 3 is the temperature. This is not as relevant in our physiology just because our body temperature is pretty standard. But if we had a very high temperature, that would sort of denature the enzyme or change the rate of movement of particles. That could also determine how fast particles are moving and whether or not they're likely to go through the membrane, but again, not as relevant in our physiology. And then number 4, the thickness of the membrane. This is another one that becomes very clinically relevant when we talk about the lungs. So the thickness of the membrane is different from the surface area, right? So we can have a lot of surface area exposed, but the membrane is thick. Ideally, in looking at the lungs, for example, the alveoli should be very thin in the wall. The walls should be very, very thin to allow for gas exchange. And as we see different types of lung diseases where that wall becomes thicker, or another example of that is fluid. If there's fluid in the lungs, it's going to behave the very same way as it would as the membrane getting thicker. So the thickness of that membrane simply means that there's more stuff in the way of particles to get through, and that is going to slow the rate of simple diffusion down. So the thickness of the membrane is the 4th factor that influences the membrane permeability, and then the membrane permeability, we said, influences the rate of simple diffusion. Okay, So here is just illustrating that. So here's another curve. So concentration gradient versus our net flux. And notice that if we have a low permeability, even if we have the same concentration gradient, we're going to see a lower movement of particles, right? Lower movement of particles. If we had a higher permeability, we're going to see a higher movement or faster rate of simple diffusion, even for the same concentration gradient. All right. Okay, we're going to skip over these checkpoint questions. You do have access to this in your PowerPoint, so I'm going to encourage you to go over this as homework, but we will come back to these and discuss them as a part of our review.